Let me give you the construction of this symmetric group S3, which is an important example for group, especially in the case of normal subgroups. So how to construct this group S3? So first step is to take a set A which contains three elements 1, 2 and 3. Now define a mapping F from A to A. The 1, 1 on 2 mapping that you can define from A to A are given as below. Number 1 is F is equal to I, that means element 1 is mapped to 1, 2 is mapped to 2, 3 is to 3. So this mapping F, which is 1, 1 on 2 is denoted by I, the identity mapping. Now number 2, 1, 1 on 2 mapping from A to A itself is this one. F is equal to 1, 2. I denote this F mapping F as 1, 2. Why? Because 1 is mapped to 2, 2 is to 1, but 3 is fixed. That is 3 is mapped to 3. So again this is a bijective mapping. Number 3 is F is equal to, the mapping F is equal to 1, 3 here, which means that the element 1 is mapped to 3 and 3 is mapped to 1, but the element 2 is fixed to 2 itself. Now number 4 is the mapping that you can define from A to A is this one. F is equal to 2, 3, which is again a 1, 1 on 2 or a bijective mapping, where you fix the element 1 to 1. That is F of 1 is equal to 1, F of 2 is 3 and F of 3 is equal to 2. So that's why it is denoted as 2, 3, which means that 1 is fixed here. In 1, 3, 2 is missing, so that means 2 is fixed or 2 is mapped to itself. And in the second one, 1, 2, here 3 is missing, so it means that the element 3 is mapped to itself. And then the other two 1, 1 on 2 mapping that you can have from A to A are this one. The fifth one is 1 is mapped to 2, 2 is mapped to 3 and 3 is mapped to 1. So that's why I denoted this F here as 1, 2, 3, which implies that 1 is mapped to 2, 2 is to 3 and 3 is to 1. And the last 1, 1 on 2 mapping or the bijective mapping you can have from A to A is this one. 1, 3, 2. That means where 1 is mapped to 3, 2 is mapped to 1 and 3 is mapped to 2. So you can see from here 1 is to 3, 3 is to 2 and 2 is mapped to 1. So these are the only 6 bijective mapping that you can have from A to A. The number of bijective mapping from A to A is 6, that is 3 factorial, and they are denoted as. In general, if a set A contained n elements, then in that case the number of bijective mapping you can have will be n factorial. So here it is 6, which is given by that 3 factorial only, and they are denoted by this notation. So the first 1, 1 on 2 mapping is the identity mapping, that the one that are denoted by I. The second one is 1, 2, that means 3 is fixed here, that is 3 is mapped to 3, 1, 3, here 2 is fixed, that is 2 is mapped to 2, and in 2, 3, 2 is to 3, 3 is to 2, and 1 is missing here, means that 1 is mapped to 1 itself. The next one is 1 is mapped to 2, 2 is to 3 and 3 is to 1, and the last one is 1, 3, 2. So these are the 6 bijective mapping that you can have from a set A to itself. Now let us show that this 1, 1 mapping, this S3, these 6 bijective mappings from A to A forms a group under the composition of mapping. That means the binary operation here will be the composition of mapping. You have done this composition of mapping in first semester, so you can just go through those notes. What is composition of mapping? That is F composite G of X is defined as F of G of X. You apply G first on that element X, and then after that you apply F on G of X. So let me just recall this one. If you go through the notes of first semester, you'll see that composition of mapping is associative. That is F composite G composite H of X is same as F composite of G composite H of X for every X belong to a set. That is F composite G composite H is same as F composite G composite H. Now, so in this case, since all these 6 elements of S3 are mapping, so therefore it will always satisfy this one, the associative property. That is, if you take any 3 mappings from this set S3, that is this one, then you will see that for example, I composite 1, 2 composite 1, 3 will be same as I composite of 1, 2 composite 1, 3. That means it will always satisfy the associative property, which is true for not only for the bijective mapping, but it is true for any mapping. So the first property of a group, the first axioms of a group has been satisfied by the elements of this S3 under the composition of mapping, the binary composition of mapping. Now only thing that this one, associative property. So associative property is always satisfied by the mapping. So that's one is clear only. So from there only we can conclude. But now we need to show the existence of identity element in this S3. What is that identity element? The element which act as this one in a group G, there must exist E belong to G such that EX should be equal to XE, which is equal to X for every X belong to G. So if I can show you the existence of an element E belong to G for which EX is equal to XE, then we can conclude that there exists an identity element in a group. Now I'll show you, okay. Now this identity I here, the identity mapping always act as an identity element of this group S3 under composition of mapping. So let me show you now this one. I composite 1, 2. So if you compose it with this one, I composite 1, 2. If I get it as 1, 2, then this and then we can show later on that 1, 2 composite I also should be equal to 1, 2. So that we can conclude that I is the identity mapping. So now just take this particular element first. I composite 1, 2. I composite I here, the identity element here means what? 1 is mapped to 1, 2 is to 2, 3 to 3. You can express this I in this way. Composite 1, 2. Now 1, 2 means 1 is mapped to 2, 2 is to 1, 3 is missing here, that means 3 is mapped to 3 itself. So take the composition of this 2 and see what will be the one. Now always remember that in a composition of mapping, when you apply F composite G of X, this is called F of G of X. You apply first this one, G on X, and then after that F on GX. So here also I need to apply first this one, the left side, and then take a composite with this one. So here you can see from here 2 is mapped to 3. But what is this 2 here? 2 here again is mapped to 2. So that means 1 is mapped to 2. Now what about this 3? This 2. 2 is mapped to 1 here. And just check, this 1 is mapped to where? 1 is mapped to 1. So that means 2 is mapped to 1. Now 3 here is fixed. 3 is mapped to 3, and then you can see from here the 3 here is mapped to where? It is mapped to 3. So 3 is, so 1, 2, 1 is to 2, 2 is to 1, and 3 is to 3. So again 3 is fixed here, which is same as 1, 2, which is same as this one. Similarly, you can show that I2 composite 1, 2 composite I. This will give you this one. You can check again from here. 1 is mapped to 1, and then here 1 is mapped to 2. So that means 1 is mapped to 2. 2 is to 2, but this 2 here is mapped to 1. So 2 is to 1. 3 is to 3, and 3 is to 3. So 3 is 3, which is again 1, 2. So we see that I composite 1, 2 is 1, 2, and 1, 2 composite I also is 1, 2. So now here in similar way you can show that I composite 1, 3 will be 1, 3. I composite 1, 2, 3 will be 1, 2, 3. I composite 2, 3 is equal to 2, 3, and so on. So this implies that this element I here will act as the identity element in this set S3 under the composition of mapping. Now this will be the table. You can construct a table here itself to show the existence of identity element and existence of inverse element. So now here I composite 1, 2, that one we are done. Now 1, 2 composite I is 1, 2. 1, 2 composite 1, 2. How will you show that 1, 2 composite 1, 2 is equal to I? That means the inverse of 1, 2 is I itself. So here again 1 is to 2, 2 is to 1, 3 is fixed, 3 is 3 composite 1, 2, that is 1 is to 2, 2 is to 1, and 3 is to 3. So this is equal to 1, 2, 3. Now 1 is to 2, and this 2 is mapped to 1. So it maps to 1. 2 is to 1, and 1 is mapped to 2. So that means 2 is mapped to 2. 3 is to 3. So 3 is to 3. So 1 is to 1, 2 is to 3 is 3, which is equal to identity. So we have identity here element. And if you take 1, 2 composite 1, 3, you can check from the notes that I have given you. It has been given in detail. 1, 2 composite 1, 3 will give you 1, 3, 2, and so on. Similarly, 1, 3 composite itself 1 3 will be I. That means the inverse of this exists and it is 1 3 itself. 2 3, the inverse of 2 3, you can see in this column it is I. So that means the inverse of 2 3 is I, and the inverse of 1 2 3 is 1 3 2. You can see it here. You can check that 1 3 composite 1 3 2 is equal to what? It is equal to 1 is to 2, 2 is 3, 3 is to 1 composite 1 is to 3, 3 is to 2, 2 is to 1. So this is 1 2 3. You can see 1 is to 3, 3 is to 1. So that means 1 is to 1. 3 is to 2 and 2 is to 3. That means 3 is mapped to 3. 2 is to 1 and 1 is to 2. That means this 2 is mapped to 2. So which is identity? So it means that the inverse of 1 2 3 is 1 3 2, and similarly the inverse of 1 3 2 is equal to 1 2 3. So under from this table you can see that I act as the identity element, and every element of this S3 has an inverse in S3 itself. So by the group axioms we can conclude that S3 under the composition of mapping forms a group. But this S3 is not commutative, because you can see that 1 2 composite 1 3. From the table you can see that 1 2 composite 1 3, this one 1 2 composite 1 3, 1 2 composite 1 3 is equal to what? It is 1 3 2. But what about 1 3 composite 1 2? 1 3 composite 1 2. That is 1 3 composite 1 2. It is 1 2 3. 1 2 3, which is not equal to this one. So this shows that S3 is not a commutative group or an abelian group. So this is the smallest group which is non-abelian, okay, because a group of order less than 6, that is 1 2 3 up to 5, are always abelian, and this is the first subgroup. So not the first subgroup, it is the first group of order equal to 6, which is not an abelian group. So hope with this explanation it is clear now, and you can go through the notes that I'm going to send you, and if you have any doubts, you please let me know.